network defense and the systems that keep us ahead. The protocols and data structures all clearly explained. With machine learning power, a new era dawns. The 8th session begins, led by the vision of Dr. Sade.
Welcome, everyone. This entire session is about combining two powerful ideas: intrusion detection and machine learning, specifically deep learning. Think of an intrusion detection system as your digital bodyguard for a network. We're going to learn how to train this bodyguard to spot bad guys using advanced learning techniques. It's a crucial topic because in today's world, security is everyone's job. Before we dive deep, I want you to hold this core idea. Everything we do in network security is a constant race between the defenders and the attackers. Deep learning is our new high-tech tool to get an edge in that race. Here's a roadmap of what we'll cover. This unit is built around 3 pillars: the data we use, like KDD99, the protocols the attacks run on, and the core concepts of network intrusion detection systems, NIDS. We'll spend a good amount of time on how this data is collected, and importantly, what's actually inside that famous KDD99 dataset. This is where we learn to speak the language of network traffic. Intrusion detection is fundamentally a classification task. Our job is to sort network connections into 2 categories: good or bad. Unlike other types of datasets that may focus on individual instances like a spam email, intrusion detection datasets focus on patterns of activities. This approach is crucial because we're often working with limited information available in network packets. An intrusion detection system, or IDS, is your network's watchman. Its role is to identify potential security breaches and to act before any serious damage occurs. It's important to note that an IDS is not just a technology, but also a product of well-defined security policies and the expertise of your administrators. It has multiple roles, like detecting rogue systems and identifying reconnaissance activities and specific attack patterns. The intrusion lifecycle outlines the steps an attacker takes to compromise a system. It starts with reconnaissance, where the attacker gathers information. Then comes initial exploitation to gain network access. This is followed by privilege escalation to gain greater system control. After that, the attacker might engage in pivoting to spread the attack. And finally, they aim for persistence to maintain access without detection. Intrusion detection systems employ various techniques to do their job. First, there's signature-based detection that works like a rulebook of known bad activities. Second, we have anomaly-based detection, which compares current activities against a normal baseline. Lastly, behaviour-based detection focuses on how an entity usually acts and flags deviations from this norm. To really understand how an IDS works, we need a quick detour to understand the fundamental building blocks of the Internet. Internet data communications. Intrusion detection systems are fundamentally looking at raw network traffic, so we need to know what that traffic looks like. We'll cover the basics like encapsulation before jumping back into the ML part. Let me talk about encapsulation, a fundamental concept in networking. Imagine a packet as a structured message that moves down a protocol stack. As it does, the packet grows in size because each layer adds its own relevant information at the beginning and end. When the packet moves up, this added information is stripped away, making it smaller. This slide is crucial. It shows host A talking to host B. Notice how each layer looks only at its part of the packet. The application layer doesn't care about the Ethernet address, and the Ethernet layer doesn't care about the application data. Only the network components like routers actually change the Ethernet and IP layers as the packet travels across the network. And this is an illustration of what's inside the nested packages: the TCP segment, the IP datagram, and the frame. We're going from the abstract down to the physical. Remember, despite all these layers and headers, at the end of the day, it's just a huge long stream of bits, ones and zeros, moving across a cable. The protocols give that stream its structure. Let's discuss the Ethernet frame format. It has several key fields like the preamble, which helps in synchronization, and the MAC address, a unique identifier. The packet type tells us it's an Ethernet frame, and the CRC field is there for error detection. Now, let's look at the datagram format. Each row represents 4 octets. We have fields like version, length, and QoS, among others. The IP can be version 4 or 6, and the second row controls fragmentation. We're moving to the TCP segment format now. Like the datagram format, each row here also represents 4 octets. Fields like source port and destination port specify the service, while the sequence and acknowledgement numbers indicate positions in the byte stream. This slide summarizes the whole process, but from the receiving host's perspective. It's a decision-making flow. Is this my MAC address? Is this my IP address? Is there a service on this port? If the answer to any of these questions is no, what happens? The packet is discarded. An IDS works by looking at these packets before this final discarding passing decision is made. Ports are endpoints of logical connections. They're specified in the TCP header and have numbers ranging from 0 to 65,535. Various services use designated ports, like DNS on port 53 and HTTP on port 80. That's the quick basics on data communications. Now that we know what a packet looks like, we can head back to intrusion detection and see how a machine learning model actually analyzes these packet features to find the bad guys. Recalling our earlier discussion, intrusion detection datasets are crucial for building predictive models. These datasets can be derived from IDS log files, with Snort being a good example. It's important to know the history of a key tool like Snort. It was born in 1998, received huge acclaim in 2009 for its open source contribution, and is now developed and maintained by Cisco. This tells you it's not just a niche academic tool, it's a professional, industry-standard piece of software. Speaking of Snort, it's an open-source network IDS. It's flexible, lightweight, and can perform real-time traffic analysis. It uses a rule-based language to detect various types of attacks and probes. Snort rules are the recipe for detection. Every rule has 2 parts, like a sentence. Rule header, the who, what, and where of the packet. Action, protocol, source, destination, IP port. This is the if this packet shows up part. Rule options, the alert message and the specific content to inspect, e.g., a specific string of code. This is the and if it contains this specific suspicious thing, then part. The options are the heart of the detection engine because they look deep into the packet data for suspicious signatures. Let's see a rule in action. This example is a classic. It says, alert me if you see a TCP packet where the source is not from our internal network, but the destination is to our internal network, targeting port 111, a common service, and the payload contains a specific sequence of bytes. So, we have a rogue packet coming from outside, trying to talk to a sensitive internal service with a specific attack signature. Sound the alarm when it happens. A quick summary of the rule header. It defines the who, where, and what of a packet. It determines the flow and direction of the connection, source IP, destination IP, ports, and importantly, what the IDS should do when the packet is found. The first thing in a rule is the rule action. This is the verb telling Snort what to do. There are 5 important default actions. Pass. Think of a traffic cop waving you through. Ignore the packet. Log. Write down the details of the packet. Alert. Generate a visible warning and log the packet. Activate dynamic. These are a pair that give Snort extra power. An activate rule fires, then turns a dynamic rule on, allowing us to track a complex multi-step attack. The rule options are where the detailed inspection happens. They are separated by 2 key characters, semicolon and colon. Semicolon separates one option keyword from the next. Colon separates the keyword from its specific value, like defining a variable, content XYZ. There are hundreds of options, and these are what give the system the ability to look inside the packet for specific suspicious patterns. Let's elaborate on the activate dynamic pair. They work together to track the multi-step attacks we saw in the intrusion lifecycle. An activate rule fires on the first suspicious step. It has a mandatory activates field. This activation turns on a dynamic rule, which then monitors for the next step of the exploit. The dynamic rule is idle until the activate rule enables it. It needs a count field to track how many times it has been triggered. This is essential for detecting sequential attack patterns. Okay, we've covered the network basics and how traditional rule-based IDSs like Snort work. We've seen that we need to find patterns in network packets. This is a massive job that is perfectly suited for machine learning. Now, we move to the ML component of our course. The KDD99 dataset categorizes each connection as either normal or a specific type of attack. It covers different categories like DOS, probe, R2L, remote to local, and U2R, user to root, each representing a different type of exploit. This slide visually reinforces the KDD99 dataset. It's massive, but it's the historical benchmark. Think of it as the hello world of intrusion detection datasets. Our deep learning models will eventually move beyond it, but it's crucial to know where the research started. The KDD99 dataset also includes derived features, which are statistics calculated based on the behavior of connections to the same host or the same service in a 2-second window. This emphasizes that these derived features are the first example of applying domain knowledge, human expertise about networks, to the data to make the machine learning task much easier and more accurate. Some attacks occur over longer periods, so the KDD99 dataset also includes host-based traffic features, using a window of 100 connections to the same host. Finally, we have content features. These look for suspicious stuff inside the data portion of the packet, like a high number of failed login attempts. Let me talk about portable executable files, PE files, which are Windows program files. This is where we apply ML to static analysis. We're moving from network traffic to malware files. This is a case study on using machine learning for static analysis of Windows PE files, which means looking at the file without running it. This is a different but equally important branch of cybersecurity. PE files are the standard blueprint for Windows programs. Inside the PE file, the section tables are critical. They are like the chapters of a book, telling us where the different pieces of a program live. Standard PE files are boringly similar. Malicious ones are often weird. Evasion techniques. Malware uses techniques like packing, compressing the code, or encryption to make the file look confusing to traditional antivirus programs. These techniques usually result in a non-standard file structure, which is a key feature for our machine learning model to detect. Another crucial feature is the section names. Some are associated with specific malicious tools or packers. Packing. If a section is packed, the code is compressed and only gets extracted and run at the very last minute. We can extract all this structural information from the PE file using handy libraries like the PE file Python library, a common tool in this field. Static analysis is our primary way to extract features from a PE file: section names, section order, entropy, and so on. We are trying to extract the file's DNA without ever running it. We can also look at what the file imports, which functions from other program libraries, DLLs, it needs to run. These imports tell us its potential behavior. This simply highlights the idea that feature extraction is universal. Static analysis on a Windows PE file, like checking its sections, is similar to analyzing the manifest file for Android malware. In both cases, we are inspecting the file's self-declared structure for clues. Here's a real-world example of this in practice from Cyberbit. They built a model to detect malicious PE files. Notice the scale of the data: around 12,000 benign and around 12,750 malicious files for training. From all that data, they extracted a massive 191 features per file. This shows you the complexity of the feature space. We analyze the imports of a PE file to infer its intent. Imports can reveal a lot about what the program is trying to do. Suspicious imports. Certain imports like create process, write process memory, or calls to crypto API for encryption decryption are red flags. If a program is importing a crypto function, it might be a malicious file trying to unpack its hidden encrypted payload. Having 191 features is too many. It introduces noise and makes the model slow. We need dimensionality reduction. They used fast correlation-based feature selection, FCBF. This is a clever way to check which features are redundant, giving the same information, and which are most relevant. And the result will be cutting the feature count from 191 down to a lean 55 features. This step is critical for faster training and better model performance. With a clean set of 55 features, they chose the random forest algorithm. Random forest, it's an ensemble method, essentially a forest of many decision trees, all voting on the outcome. This makes it robust. Parameters? They tuned the parameters using a cross-validation technique, selecting things like 2,000 trees and using information gain as the impurity criterion to ensure the model was optimized for their data. After training, they looked back at the model and asked, which features mattered most? Top features. Features related to section names and permissions were most important. This confirms our initial idea. Malware uses suspicious names and permissions, like write permissions, due to packing. Suspicious imports. They cleverly grouped API functions into categories: evasion, encryption, to teach the model about the type of malicious activity, rather than overfitting to a specific function name. How do we select the best model? We want a high true positive rate, catching bad files, and a low false positive rate, not accidentally blocking a good file. Voter trees. They use the concept of percentage of voter trees, which is the minimum fraction of the 2,000 trees required to vote malicious to flag the file. ROC analysis. They used a receiver operating characteristic, ROC curve, to plot the true positive rate versus the false positive rate to find the perfect balance. This slide shows the final, crucial decision. The team decided that their ideal point was one with no more than 5 false positives per period, 0.001 FPR. The threshold. To achieve this goal, the optimal threshold was determined to be 85%. If at least 85% of the random forest's 2,000 trees vote malicious, the system flags it. This gave them a 70.6% true positive rate, which is a good trade-off for such a low false positive rate. This is a critique of the previous choice. The team prioritized minimizing false positives, which is often desired in authentication systems. However, in malware detection, we often want to prioritize minimizing false negatives, the missed attacks. A missed attack is often more dangerous than a false alarm. One is the correct balance in security. Finally, the model in action, the loop. When the system flags a file as malicious, it generates an alert for a human analyst. If the analyst confirms it, the file is deleted, and its features are added back to the dataset for the next training cycle. This is a continuous feedback loop that ensures the machine learning model keeps learning and stays effective against new, evolving malware. Thank you all for joining me. We covered a lot today, from the fundamentals of network packets and Snort rules to the advanced applications of machine learning for detecting intrusions in both network traffic and executable files. I hope you found this deep dive into cybersecurity both informative and engaging. Keep studying, keep asking questions, and I look forward to seeing you all next time as we continue our journey into deep learning and security.